Okay, so this was the general equation that we obtained for the sphere independent of the hydrodynamic region. And then I asked you to uh, basically limit it to the creeping flow region and derive the familiar Stokes expression. So can you all do that, please? So essentially, what you had to find out is the constant which rings the Reynolds number and the CD value and the inverse proportional dependence of CD on RE, which is the hallmark of that region, right? So it had something like this. So at low Reynolds number, the drag coefficient varies inversely with Reynolds number of the particle Reynolds number, and the numerical value was 24, right? So please see that you should all derive these three relationships. The bottom one is what we started out with, okay? So please do that. So essentially, if we were to plot the drag coefficient and the Reynolds number on log-log plot, we will get a straight line in the creeping flow region up to Reynolds number 1. Okay. And then I asked you to find at Reynolds number 1 what is the value from the general expression that you get for CD and compare it with the 24 value that you get if RE is put 1 in this idealized expression for the creeping flow region. CD is equal to 24 by 1. Okay, and I asked you to find the percentage error. So these are the two questions that everybody must be able to do. So first derive these three equations and try and tabulate them for the low Reynolds number region below 1. So 10 to the power minus 5 to 1. And find me the maximum error and tell me what you get. I just indicated how you should do it. And if somebody has done this, I would challenge them to go to the high Reynolds number region beyond the 2100 RE, and that is called Newtonian regime, just as this was the Stokesian regime below RE less than 1 until 10 to the power minus 5. So something like 2000 to 10 to the power 5 or 2 into 10 to the power 5 we'll call as Newton's regime. And what constancy or what relationship do you expect for the drag coefficient on the hydrodynamics and on the Reynolds number? Can you think on that? And then can you use that to derive me three more equations like this for the high Reynolds number turbulent flow region? See, turbulent flow has a very specific signature up to 2 into 10 to the power 5 Reynolds number. So please think what this could be. Are my questions clear? So my questions are threefold. Firstly, take the general equation for the maximal velocity with acceleration term 0, limit that to the geometry of a sphere, then get the general equation with the 4 by 3 numerical value inside the square root. That's valid independent of Reynolds number or hydrodynamics. Then limit that further to RE less than 1 and derive these three equations that are on your screen. That was question 1. Second, find the maximum error that is incurred, find the maximum error that you would obtain if you were to idealize everything at the extremity of RE1 by this simple equation that is given there, CD is 24 by RE, and compare that with what is actually found experimentally, which I told last class, or what you would find from the general equation. Not that for the Stokesian, but the general equation within the under root with the 4 by 3. And tell me what kind of errors you get if you were to assume Stokesian at the limit of extremity of RE equal to 1. So this was the viscous flow region. Now assume that inertial terms is point number 3, question 3. Assume that inertial forces dominate, which I'm calling Newtonian regime. Then what would you expect as a constancy or as a relationship for the drag force as a function of the Reynolds number? That is beyond the laminar flow region until, let us say, a Reynolds number of 10 to the power 5. Independent of shape, what do you expect? Whether it's a sphere, cylinder, disc, cube, what is found by experiment? What do you think could be found by experiment? So this a relationship, if we can identify, then we can use the same approach that you have used to derive the 3 equations on your screen for the low Reynolds number values, so region. You can use that the same for the Newtonian regime. And then you will get 3 more equations like this. So this much I want you to try. Well, the good thing is for free particle settling, single particle, you can actually derive these things exactly. The moment we go to a packed bed, which we want to do, I mean, it will be very difficult to do this by theory, okay? There is no such general solution. So we have to take recourse to experimental data and all of those Plummer equations and um, other equations for packed fluidized beds are derived like that. So it's very difficult for us to do much with pen and paper. Similarly, Karman equation, they are all derived by experimental approaches. And then we simplify them, and then we get empirical equations for packed beds. Okay. So, but the good thing here is you can do everything exactly. So I kind of like it. So question number 1, these 3 equations, tabulate them and derive them yourself. Question number 2, what is the maximum error incurred with this approximation? I have given you what you get by experiment or by the general equation and what you find by the Stokesian, which is 24. Okay, find the error. And then we need to go to the Newtonian regime and do the same and derive 3 more equations. These are our 3 questions. How will you find the maximum error? You will find what is the CD by the Stokes equation. You will determine the CD from the general equation for spheres or from whatever is found by experiment. Then you will see the functionality of how CD appears with respect to the terminal velocity, and then tell what is the what is the error incurred in the determination of Umax based on the functionality with respect to the drag coefficient. Now, we can do a very similar exercise for the other, for the one we did for Stokesian, we can do the same for Newtonian. The two poles of regimes, I would say. What is found experimentally is that whatever be the shape of the particle, irrespective of that, the Reynolds number, when it varies between 1000 to 2 into 10 to the power plus 5, this drag coefficient reaches an asymptotic value. It becomes constant. Okay. So and this constant value can be determined by experiment, by doing this on a number of settling chambers or wind tunnels, and this works out to be for a sphere 0.44 CD value. So if we take that, so what used to be 24 now has decreased to 0.44. If we take that value, it's a very good approximation, shape independent approximation for the Newtonian region between Reynolds number 1000 to 200,000. Okay, so the Reynolds number is approximately constant. That is what this slide. Now use this constancy. This is what this slide is showing. It's constant. And I gave you the value of that 0.44. Now use that and derive me 3 more equations which will replace the Stokesian regime equations with this Newtonian regime equations. Okay, I think I have clearly told what needs to be done, and I will indicate you later. You can write it down or take a look at that slide and see whether your derivation works out. Okay, the maximum error that you get in the Stokesian, to answer the question number 2, is approximately 5%. So please check that you get that value. Okay, 5%. So now go to the third problem. Go to the turbulent flow Newtonian fluid region. The Reynolds number range is indicated in the slide, 1000 to 200,000. In this region, use the constancy of the drag coefficient and derive me 3 more equations, which are the counterpart equations. The counterpart equations of the Stokesian regime for this new Newtonian, for this high RE turbulent flow Newtonian region. So we are going step by step. Okay, now so what you should get, I will present you on the screen. You can tabulate these. Right. So I've just summarized you the two regimes. Stokes RE less than 1, Newtonian 1000 less than RE less than 200,000. And these are the equations that you ought to get. So the coefficient, the drag force, and the maximal velocity. Please do this and check that this is correct. So this is an exact calculation, right? By solving the equations of motion, which we could do for this free settling single particle in an infinite fluid, we get these exact dependencies and these exact relationships. See, this is a very different relationship from the Stokesian, because in the quadratic dependence of the terminal condition velocity on the particle diameter, the quadratic dependence is now replaced by a square root dependence. So completely different scaling, right? That is a hallmark again. This half power dependence on the diameter of the particle, spherical particle, is a hallmark of the turbulent flow Newtonian region equations. Very well. Now, what is it that we have done? We have done RE less than 1, we have done RE greater than 1000, all the way to 10 to the power 5, 2 into 10 to the power 5 actually. Now, we are left with the intermediate region between Reynolds number 1 and 1000. What would you advocate for that region? See, you have solved for these two regions, Stokes region and Newtonian region, and you have got these exact equations. What should we do for the intermediate region? A more interesting question. So why don't you all tabulate me the two poles, the Stokes region equations for drag coefficient, terminal condition velocity, and drag force. Similarly, do the same, tabulate the CD, FD, and UT for the Newtonian region for turbulent flow. So we'll have those 6 equations. And then now think what to do for the intermediate region. So that's the next slide. What a question mark. 1 less than RE less than 2000. Let's call that intermediate region. What should we do there? I am assuming that you have got the two poles of for the Newtons as well as the Stokeses. So now you can pay attention, transfer your focus to this very important Reynolds number range, which is cannot be classified as Newtonian nor is it Stokesian. We have called it intermediate region, and Reynolds number range is also given to you on the slide. But we don't know how to evaluate the maximal velocity, how to evaluate the drag force in this region. What should we do? It's the question I am wanted to ask and actually solve today, but I don't know if we can solve it. But I will indicate a solution. I shall indicate a solution definitely, but attendance is somewhat low today. So this is a very important point. So looks like we have to wind up next time. I shall, however, indicate a solution, and then you guys can think on that. So as I said, you can neither model drag force, drag coefficient, etc. in the intermediate Reynolds number region. You can't treat it as Stokes flow. I already told you that Re equal to 1, we are making 5% error. If you go beyond, the error will start accumulating and increasing. Okay, so I won't advocate using the Stokesian. The same thing, if you were to assume a constancy of the CD, as you do for the Newton's turbulent flow regime, Newtonian region, or where Newton's law type thing applies, I would not advocate that either. For the intermediate region between Reynolds number 1 and 2000. So our question that we want to address today is what should we do for what to do for this region? Because if we can complete this region, then we have the entire 10 decades of Reynolds number. That was what we wanted to start out with, right? From 10 to the power minus 5 to 10 to the power plus 5. So a hint is provided by the next slide, which is taken from Perry and Chilton's handbook, with the drag coefficient CD on the y-axis plotted as a function of Reynolds number on the x-axis. It is in logarithmic coordinates, double log plot. So it goes, it straddles that range of 10 decades of Reynolds number, 10 to the power minus 5 to 10 to the power plus 5. And as you can see, there is a tremendous reduction of 5 orders of magnitude of the drag coefficient as you go from 10 to the power minus 5 Reynolds number to turbulent flow. Huge reduction in drag. So obviously, if at Re equal to 1, if you model something by the viscous drag that was there at that, and try to transpose that to higher Re, you will make a lot of error. Similarly, if you were to take the constant C or of CD of 0.44, which is in dimensionless units, and extrapolate that to where the viscous forces dominate, you will make several orders of magnitude, you will be off. Now, the problem is in this intermediate region, neither is the CD-RE relationship a straight line in log-log coordinates, nor is it constant. It's gradually decreasing and asymptoting to that constant value. and that value is given to you. I gave you the constant value for a sphere. It's also given to you for two other shapes, cylinder and discs, in that graph. So this is all coming from Von Karman, a great fluid mechanicist and aeronautical engineer. His work on fluid in wind tunnels, and essentially it has taken almost 30-40 years of experimental work to reach this diagram that is shown in Perry and Chilton's Chemical Engineers Handbook. So the good thing is, from this experimental data, I mean, this graph is generated by experiment. We know the relationship of CD with RE at every RE, right? The numerical values are available for the drag coefficient at each Reynolds number, because they are plotted as a function of Reynolds number over a very large range. Now, the question for you is, how are you going to use this functionality, which is there in your graph, and you know the numerical values, yet you cannot represent it by a straight line or by a constancy, because in the intermediate region, it's not fitting any such obvious relationship. How are you going to get the exact values of the terminal velocity? That is the question that I want to leave you with. Ideally, we wanted to solve it today, but people are very few today, and I think you should think it out for yourself. And I have indicated a solution. And the indication is, look at the graph, see how that variation is. Don't try to curve fit it. The numerical values are available to you from that graph. In other words, the relationship is there in a graphical format. How are you going to use that relationship between the x and the y axis, x and the y variables, the y variable and the independent variable x in this graph, to determine the drag force and the maximal velocity in this intermediate region? Okay, so that is my question for today. So let me summarize what we have done up till now. We started from a very general equations of motion. We solved it for the accelerating frame, independent of the force field. Then we restricted it to du dt tends to 0. We neglected that term. We got another general expression. And then we said, well, this is shape independent. Let's restrict it that to a sphere. We restricted it. We got that 4/3 expression within the quadratic, within the square root term. Then we said, well, let us look at this, how this CD, which is there, because all the hydrodynamics was not included, it was there in that CD. And we said, let's look at how that changes with the Reynolds number. We did that for the Stokes region. We did that for Newton's region. And you got exact relationships for the terminal condition velocity, the CD, and the drag force. Okay, so 6 equations. Now I want you to do the same for the intermediate region, but this one is not is just one step further. You have to use your gray cells. Okay, so if you can just suggest me what your solution is, or just propose a way to solve this intermediate region problem, that I'll be very grateful, rather than my having to exactly solve it. Okay, so this is your assignment. And next time I would like you to everybody to submit something on that. How are you going to solve this problem? Okay, question is clear. How will you do the intermediate region problem? Given the CD-RE functionality and all the other things that we discussed. Until now, okay? So I think next time, let us try to wind this, and this is still free settling. Uh, if possible, I wanted to do some hindered settling problem, but it will probably take too much. Let us see. Let us see what we can do. And either way, next week we will wind this up and then move to something much more complex, another topic. Okay. Any questions? Okay, look at the graph and the functionality that I have put on the current slide and come up with indication of a solution for this intermediate region where we can't approximate something by a straight line, nor can we approximate it by a constancy in the coefficient of drag. How should we do this? And I think this is a very important type of problem that we encounter in all engineerings, not just chemical, but fluid particle mechanics, but in pretty much in all types of engineering analysis of systems. So I would like to also delve a bit into such type of problems and let us give them a particular name, and I think they recur again and again and again. Okay, think on it and I shall discuss that next time. All right, thank you so much then.